Our project is titled An Environmentally Conscious Mask. In this project, we explore different mask materials and how well they contain respiratory droplets to minimize the spread of COVID-19. We developed a process to make these masks and plan on continuing this project to further our research and improve our process. To start the project, we needed a goal or central idea to focus our research on. The engineering goal was to design and construct a mask that is both effective at source control and environmentally friendly. We wanted to address how the increase in disposable masks will have inevitable environmental consequences. Rising temperatures will lead to an increased risk of disease, forming a climate pandemic paradox. To break this chain, we need to design medical equipment that is more environmentally conscious.
To address this problem, we researched the qualifications of biodegradability, components of a mask, and factors that form an effective mask. The expected outcome we came to was a 3-layered mask: a hydrophilic inner layer, a hydrophilic or hydrophobic middle layer, and a hydrophobic outer layer. Ideally, the materials would have a low carbon footprint, and the mask as a whole would have minimal impact on the environment after disposal.
To execute this goal, we had to establish some criteria: breathability, filtration, and water resistance. We also considered the material and method's environmental impact with designing the product, such as carbon footprint, energy consumption, and biodegradability.
For example, we found 8 stalks of bamboo for $20 at a local supplier, and bamboo only takes 4 to 6 months to decompose. We define biodegradable as any material that can degrade within a year.
We started brainstorming possible solutions to our goal. While I researched existing mask solutions and materials, Daniel investigated the environmental impacts of masks. In addition to this, we looked into existing mask tests to see how mask efficacy was determined and developed our experiments using these principles.
Using the research to guide our product design, we were able to test paper, pond straw, bamboo, wood, and combinations with beeswax and layering.
To create a good mask, the WHO recommends 3 layers: a hydrophobic outer layer, a hydrophilic inner layer, and an optional hydrophobic or hydrophilic layer in the middle. With that said, the project we created can be tailored to fit these different guidelines. The paper is hydrophilic, comfortable, and easy to form fit. The middle layer could be pond straw, bamboo, or an additional filter that is separately inserted and disposed of. The last layer, beeswax, is the hydrophilic component to prevent droplets from penetrating the mask. In order to test the different criteria, we designed 3 tests to evaluate each variable. The first step was the candle test, which evaluates the breathability of each mask based on the flame condition after blown on. This determines if the mask is too thick or thin, which may impair one's breathing or efficacy. The second test was a spray test. This was indicative of filtration and spray distance, which is important when considering an individual's transmission radius. The last test was the water resistance test, which measured the difference in material and water mass after being exposed to each other. This is important for evaluating the effectiveness of the outer layer, as it should inhibit incoming droplets. Overall, these tests gave us a good indication of each mask material's efficacy.
Our goal was to construct a mask that is biodegradable, accessible, cost-effective, and applicable to large scales. We wanted to develop a product that is effective at source control in a public setting, not necessarily in a medical setting.
The solution we created based on the tests was successful. The results from the breathability test show that most of the materials are effective at managing airflow. The results from the spray test indicate that a combination of pond straw, paper, and beeswax produces the least amount of transmission. Furthermore, the water resistance test observes that beeswax infused with another natural material is a good way to increase its hydrophobicity. The data from different materials indicate that the product was successful in regards to breathability, filtration, and water resistance.
To determine the best prototype, we quantified, averaged, and compared the data over all 3 tests for every material. We concluded that a paper, pond straw, and beeswax mask is the best model moving forward.
Although we were able to conduct multiple tests, there are still some criteria that would provide more data to create a better product. For example, we could use Sherilyn imaging to better understand how the mask impacts the airflow. Other inaccessible standardized testing methods could be used to indicate mask efficacy to a more specific and universal standard. Another criteria that could be tested is the life expectancy of COVID-19 on the mask materials, indicating how dangerous the material will be after disposal. Furthermore, the biodegradability of the material could be measured to get a clear understanding of how the different materials compare to each other. The one aspect where we applied special analysis was during the water resistance experiment, where an equation was created to compare the multiple data sets with one value. The equation was water resistance equals initial water minus final water plus difference in mask weight, where everything is measured in grams.
From the data, it was clear that the pond straw, paper, and beeswax combination performed performed the best in all the tests. For example, the combination scored a 3 at all distances from the candle, showing good air control. Furthermore, the average spray distance of water droplets from the pond straw, paper, and beeswax mask was 0 centimeters, tied for the lowest distance. This value reflects how well the product contains respiratory droplets. Lastly, the pond straw and beeswax combination earned a score of 0 grams, the best performing material in the dataset. However, this project was not without its limitations. The spray test contained a systematic issue from the procedure.
The spray droplets were marked through visual indication, and even though that process was improved upon through recording video footage, there wasn't enough time to review all the footage to confirm with the visual observations. Another systematic error occurred with the making of the wood masks. Though the results indicated that the mask was not a good material, we also recognized that not all the masks were made with the same quality, which is something to look into. We were also comparing datasets from 2 different testing periods, one of which was improved on from the initial round. This should be considered when evaluating the results of both rounds to establish a conclusion.
In addition to testing limitations, there were also several other factors that required management. For example, we were very limited on time, as everything from finding materials to producing the mask took longer in a social distancing setting. Furthermore, many of the equipment used to test mask efficacy were inaccessible, making the evaluation of the product more nuanced. Lastly, because mask making is a complex process and we were experimenting with new mask materials, there was a lot of trial and error to identify a process that worked in a home environment. This required more time, thus putting additional pressure. The outcome of this experiment provides findings that are consistent with that of other research. An effective mask should contain multiple layers, particularly a hydrophilic inside and a hydrophobic outside.
Looking to the future, obtaining expensive equipment that was not available in this project could create more precise comparisons between prototypes. Since it has been established that the most effective biodegradable mask is one of 2 hydrophilic inner layers and a hydrophobic outer layer, further testing could be done of different hydrophobic layers in comparison to beeswax. Materials like banana fibers and candelilla wax may be good alternatives to beeswax. Other procedural implementations, such as fusing paper and other materials while drying, using a bowl to improve layer consistency, putting aluminum or saran wrap between the material and sieve, and using a flat sieve for more flexibility could streamline production. Lastly, we want to continue reaching out to scientists, doctors, researchers, and mask companies for professional feedback and opportunities.
The results of this experiment can be applied to many different fields. For example, one application is finding more environmentally friendly materials to substitute single-use items, specifically medical equipment.
These disposable biodegradable masks could be widely distributed through automated stands at public places like shopping malls, grocery stores, and parks, and streamlined for mass production. Furthermore,
the findings of this project could be extended to broader fields, like environmental alternatives to traditional products. We also hope that our conclusions spark conversation on replacing conventional items like tableware with human-safe yet resourceful materials. The mask-making methods used could also influence how medical facilities think about their equipment, adopting biodegradable alternatives instead of relying on the existing surgical masks, which are single-use and difficult to dispose of. They may also consider investing in other biodegradable research for disposable gloves, hairnets, and other PPE. As COVID-19 overtook our daily lives in March 2020, effort and attention to combat climate change was put on hold to rightfully combat the virus. Many people believed that COVID-19 brought substantial environmental benefits due to international shutdowns. As economies began to reopen and masks rose in demand, waste also increased. Disposable masks will continue to pile in landfills, erode in parks, and kill marine life due to their polymer design that takes hundreds of years to decompose. Alex and I were inspired to create an environmentally conscious mask due to the significant environmental impact disposable PPE has caused during this pandemic. In July, an estimated 129 billion face masks per month were disposed of into the environment, and that number has since grown. Thus, if all disposable masks were replaced with the effective biodegradable mask that we designed, an estimated 497,000 tons of waste per month would be avoided from entering the environment. Thank you.